Hi, welcome to part 2 of the Mxx Energizer Stealth board repair. My name is Craig and I'll be your host in this vlog where I discuss and rate a typical South African craft beer that you might find in our markets, as well as attempt to repair an electronic consumer good that you might find in the average South African home. Today on review, I don't know why, I have a Darling Brew glass. I'm not sure where I got this, but we're going to rate the Bone Crusher style 24A Vitby. Very nice, refreshing drink. We'll see how they match up. In part 1, we looked at the Energizer Stealth board and we found a few things wrong with it, namely one of the diodes in the bridge rectifier had gone and 2 little switching transistors. Today we're going to build a we're going to design and build a power circuit so that we can turn this thing on and see if we have any other faults. There is a little bit of maths involved. Trust me, I'm going to make it as simple as possible. Stick with me and we'll take it from there. See you on the bench. So of course today's video we have to design and build some sort of power supply that can power this. Now I just want to draw your attention to these capacitors. You see it's got a 35 volt rating. If you remember, our AC input came in there, through our diodes down here, through these caps, eventually onto our switching transformer. In the previous video I said that this is not built for mains AC, and we can see that these caps are only rated for 35 volts. So we're going to do a bit of reverse engineering, and to do that we need to do a little bit of maths, and then we'll design a circuit and I'll show you how we can do some very basic maths to do a few little things that we need. Let's get onto the paper. And there we have our Darling Brew on the bench. Darling Brew's label, the Bone Crusher, they reckon it's 5.2% ABV beer, brewed in the Belgian ale category of Vitbier. Vitbier, according to the BJCP 2015 style guidelines, the overall impression of the beer should be refreshing, elegant, tasty, moderate strength, wheat-based ale. The Darling Brew, the slow beer, is one of the first craft beers I tasted about 5 years ago, and it's always stuck with me. I don't drink it often, but occasionally when I do get it, sometimes I feel that the recipe's changed and they've tried something different, and then at other times I feel it's exactly the same. So that's just me and my crazy mind. Anyway, Vitbier typically is not a strong beer. Anything from 4.5% to 5.5%. As we can see, this has got a pale yellow, pale straw color. Now I'm expecting out of this beer some tarty citric notes. I'm not expecting a beer that will be heavy and like a dessert beer type thing. I'm expecting a refreshing drink. So as we go along, we'll of course make notes and we'll discuss it at the end. In part 1 we saw that a diode, we draw a little diode. If we put a positive voltage here, a negative voltage here, and as long as this is more positive with respect to that, the diode will carry current. Now I went and I looked at the data sheets for the diodes that we actually have installed, the S3B diodes, and they have a forward voltage of 1.15 volts. So that means if you put 1.15 volts more here than what that is, this diode will now conduct current. The problem with that diode is it has a maximum recurrent peak reverse voltage. In other words, if I put a voltage here that's more positive of 100 volts, then this diode will collapse. So that's our first clue, that circuit is not rated for AC mains. The second clue is the capacitors. Now, we didn't talk about capacitors, but we will briefly now. The capacitor is simply two plates with an insulating material, usually called a dielectric, and all a capacitor does in a DC circuit, if you apply voltage, the capacitor will charge up, and once it's fully charged, it will resist a change in voltage. In other words, if this side starts to dip, the capacitor will release its charge to bring the voltage back up. And when the input power is restored again, the capacitor will charge up again. The problem with these capacitors that we saw, they're rated at 35 volts. Now, typically in design terms, we don't, if we design a circuit for 24 volts, we don't put a 24 volt capacitor in. Not that you would get something like that. You would normally double the voltage rating of the capacitor. This is to handle any spikes or anything like that that comes through, because capacitors do not like over voltage either. They spew their guts out. And the capacitors that we saw on the board are electrolytic capacitors. They're filled with a resin epoxy that's the insulator, and they really can make a mess on your board. So typically when we design a circuit, we would ask, or we would say, if I have 12 volts, then I want at least a 24 volt capacitor in on the voltage rating. So I'm going to make a little bit of assumption so we can do a bit of reverse engineering here. We're going to say the capacitors are rated at 35 volts. We're going to divide that by 2. That should give us 17.5 volts. If you don't believe me, we can do it on a calculator. Okay, so 17.5 volts. One thing that we have to understand about our AC wave is we looked at something like that. Now we're looking at the, not the peak to peak value. In other words, we look at a thing called RMS voltage, which is the root mean square value of that sine wave. The problem is when you come onto the DC side and you've converted that through your bridge rectifier, and you've done that and you've filtered it out, you're actually just dealing with peak. So to get that, we divide by the root of 2, and that gives us 12.374 volt. Now that looks familiar, because normally with these installations they might have a battery bank or whatever, and a battery bank would come in values of 12, 24, etc, etc. So I suspect this is our AC input, and what I suspect is what they're doing is they're taking a battery backup and they're inverting the battery backup. In other words, they're taking a battery that's giving you this, they're inverting it, and they're putting it back to AC. We're not going to get into that here. what we're going to do is we're going to design a circuit that can give us 12 volts. We're going to do a little bit of maths. We'll keep it very simple. Okay, so if we've got AC and we've got 230 volt AC, we need some device that can convert that 230 volt AC and step it down. We have a simple thing called a transformer that can do that. So we're going to put in a little transformer here. And we have our secondary side here, and off we go. This is going to be 230 volt AC, and this will be stepped down to whatever we can. We'll have a look at what parts we've got, and we'll take it from there. But we need some sort of protection here, so I'm going to put in a fuse, and we need to be able to switch this off. I'm going to call that our live and our neutral. We can switch it off. We've got a fuse to protect it against short circuit in case we make a cock up. And we've got our secondary side. So I'm just going to move the camera and everything to get a better shot, and I'm going to show you what we do have. On our board we can see this little component. That's a transformer. It's a 230 volt AC, 50 or 60 hertz, and it's got two outputs, two secondary sides, both 9 volts. Now we need 12 volts. Unfortunately, the two 9s, or an individual 9, is not going to give us what we want. They can give us a power of about 1.7 VA per secondary side winding. So if we move that to one side and then we draw, what do we actually have here? We have a primary, we have one secondary and one secondary. I'm just going to mark these like this with these little dots. Those are our indicators of the start of the winding, and that's going to be quite important for us because we can do a few things with this secondary side. If we were to, let's just do this. This is going to give us 9 volt AC. That's going to give us 9 volt AC. Now, if you've ever played with batteries, then you would know if we put 2 batteries in series, we can double the voltage. So if I take that as an output, I tie that output of that winding to that input of that winding, and I take that as an output, we'll get 18 volts AC. If I had to tie them in parallel, in other words that one to that one and that one to that one, I would have the same voltage, I would just double the power. So they were 1.75 VA. I still only have 1.75 VA because I put them in series. If I'd put them in parallel, I would have kept the voltage, but I would have doubled the power. We're not too worried about the power at the moment. We're more worried that we can deliver the voltage. So if we look at this, let's design a simple circuit around it. So with our simple transformer that we have in mind and the components on that I have on hand, I'm going to do this. We're going to come in from AC mains. We're going to go through a switch, through our transformer, and because I have a double pole switch, we're going to switch both the live and the neutral off. and we're going to go down neutral, live, neutral. We're going to put a fuse here. We'll have our transformer. We're going to have our output. We're going to have one coil or one winding tied to the second winding. And we're going to have something that can give us, at that point, 18 volts AC. But how about, we'd like to know if this thing's switched on. Let's put a little resistor in, and we'll explain why. We're going to put a little LED in, and it looks the same as a diode, except it looks like that. And I'm going to put a capacitor in. Now, why am I doing this? Well, if we remember, the diode's got a forward voltage to switch it on. We're going to design this circuit so that only a certain amount of current can flow through there. That will give this a resistance. So we're going to call it RLED. If we remember, our capacitor in the DC circuit blocks DC voltage. It doesn't like to see a change in DC voltage. In an AC circuit, it's dependent on the frequency. In this case, in South Africa, we're dealing with 230 volts AC at 50 Hertz. And you'll see very soon why it becomes apparent that we can use a capacitor as a resistor, and why in an AC circuit it might be better to use a capacitor instead of a resistor. Let's think back to standard 6 maths, physics or something like that. You learned a formula called P equals VI. Power equals voltage times the current. Let's assume we had 230 volts AC and we wanted 15 milliamp, which is 0.015. That gives us a whole 3.45 watts of power that we have to lose. So if we put a resistor in here that we wanted to drop, well, we put it on the primary side, that we wanted to drop that whole voltage at 15 milliamp, we'd use quite a powerful high wattage rated resistor, which is quite expensive. But because of the way a capacitor works, a capacitor doesn't have much resistance, and well, compared to a normal resistor, and that can come and play into our favor. So we have another formula, R equals V over I, or V equals IR. If we substitute that V, we're going to end up with P equals I times R, or P equals I squared R. Another way to derive power. Now, when we talk about power, it's very important to understand that this is something we're losing to the circuit. It's heat that is dissipated from the component. It's gone. It makes our circuit less efficient. So to do this solely with resistors, is not a good idea. A capacitance has a little bit of resistance. If we come down here and we draw a capacitor again, it's got a thing called an equivalent series resistance, an equivalent series inductance, and there's our capacitor. That little bit of resistance comes from the length of the leads, the material of the makeup and all that, but it is so tiny in comparison to an actual resistor that the heat loss, if we look at this P equals I squared R, it is tiny. So our capacitor's loss or energy loss in the circuit makes it more efficient than a resistor. We do need the resistor in this case, and that's because of the dynamics of an AC circuit. If our AC circuit is doing that, unless we're switching on there and there and there, we're actually switching where there is current, because the current follows the voltage in that sine wave. That current will kill our LED. So that's why we're putting the resistor there, just to limit that inrush. So we've got 18 volts, and we need to do a little bit of maths to calculate what will be R1, what will be its resistor value, what will be the resistance of the LED, and what value capacitance do we need. We'll be right back with that. I must say, our darling brew is going down quite well. The Bone Crusher. It's very tart beer. Very acidic. And it's got a quite a nice aroma, like cotton spun candy floss when you were kids and you went off to the fun fair or whatever, and they used to do all that candy floss stuff. It smells very, very similar to that. Very, very well done. I'm very, very impressed. But I digress. Let's get on to the maths. What we know is we've got 18 volts. We do know that this LED needs 3 volts to switch on. So I'm going to say VLED equals 3 volts. Current in a circuit like this, in a series circuit, is equal. It's the same at that point, the same at that point, the same at that point, the same at that point. The only thing that changes is the voltage. I want 15 milliamp, which is 0.015 amp. If I want the total resistance of that circuit, R total. In AC, we call this impedance. It's the sum of the capacitance contribution, it's the sum of the resistive contribution, it's the sum of the inductive contribution. We're not going to worry about inductors for now, but it's the capacitive reactance with the resistive component, and that will give us our impedance, as we call it in the AC side. But impedance is defined as Z. We can still work out with simple Ohm's law, R equals V over I, what we require as a resistor. We know we've got 18 volts, we've got 15 milliamp. I don't know if I should, probably, yeah. Let's put it here. So we need 1,200 ohms of resistance. Now what we did say, we know our LED needs 3 volts. And we want 15 milliamps through the circuit. So what is the resistive contribution of the LED? Is the 3 volts divided by the 15 milliamp. Three divided by. So the resistance of the LED is 200 ohm. Now, bear with me because this is pure resistance. How about we put a 100 ohm resistor here? Let's make it 100 ohm, and it'll become apparent later why we want to do that. So let's just make R1 100 ohm. That means our total resistive portion, in other words the LED and the resistor, is going to be R total, or let's call it that for now, is R LED plus R1 is the 200 plus the 100 is the 300 ohm. We need to make up 1,200 ohm. Now, when you're working with a purely resistive component, a resistor LED, that's fine. In an AC circuit we can use Ohm's law, but we can't do that in an AC circuit when we've got capacitance or inductance. Now, we're not going to worry about inductance. All we're worried about is capacitance. Capacitance is how does the capacitor react to the AC voltage in the circuit. And there's a formula for that, very simple. Let's just move our book up. The formula for capacitive reactance we call Xc equals 1 over 2 pi Fc. 2 pi, straightforward, frequency times the capacitance. And as we can see, the reactance of the capacitor is dependent on the frequency. If the capacitance stays constant as the frequency change, the reactance will change. We need to work out our impedance. The formula for impedance is equal to the square root of our resistance squared plus the inductive reactance minus the capacitive reactance squared. Well, we don't have any inductive reactance that we're taking into account in the circuit. A negative squared is a positive, so we can simplify this and we can do this. R squared plus Xc squared. We need to find out what value capacitor we need to put in up here. We know what our R squared is. We know what our Z is. We need 1,200 ohm. So we fudge the maths and move it around. 1,200 equals 300 squared plus Xc squared. We rearrange that formula and we do the maths. let's see, 1200 x squared minus 300 x squared rooted. We need 1162 ohms. Of capacitive reactance. If we come back to this formula, if we need to know the capacitance, we can substitute this around again. The capacitance is equal to 1 over 2 pi frequency times the capacitive reactance. So we put that into our calculator. We've got our capacitive reactance times 50, because we're working with 50 hertz, times pi times 2, and we want the reciprocal of that. We need 2.74 microfarad. You see, it's to the power of minus 6. Instead of me writing 0.00000, in engineering we work with it like this. So if we put in 2.74 microfarad of capacitance over here, plus our 300 ohms, 200 ohm contributed by the LED, 100 ohm by the resistor, that will give us 1200 ohm impedance. Unfortunately for us, we don't get a capacitance value of 2.74. But what happens if I make the capacitance 3 microfarad? So let's put in a capacitance of 3 microfarad, because that we can build up. We can't do 2.74 without a lot of digging around. So let's see what that's going to give us. X equals 1 over 2 times pi times the frequency times the capacitance. X equals 1 over 2 pi times 50 times 3 microfarad. So 2 times pi times 50 times 3 microfarad. The reciprocal of that gives us 1061 ohms. How will that affect our circuit? We just bring this down a little bit. Well, as we know, our impedance is equal to the resistance squared plus Xc squared. So it's the root of 300 squared plus 1061 squared. And if we do the maths, plus 300 squared, and we want the root of that, well, then we're going to get 1103. Okay, great. How does that affect our current in our circuit? Well, we have our impedance, which is now equal to R. So R equals V over I, or I equals V over R. So I is equal to 18 divided by 1103, which would give us 16.319 milliamp. Sorry about that. Perfect. I'm happy with that. Why did I choose 15 milliamp? The LED can handle up to, I think, about 25 milliamp before it blows. I don't want it to glow too bright, and I don't want it to be too dim. So 15 milliamp is a nice ballpark figure. So if we draw a circuit now and we put in our values, we have our switch, we have our fuse, we have our transformer, we have another switch because it's a double pole, double throw, which is what I had on hand. We have our two secondary windings, which we're going to bridge. We're going to come down with the resistor, we're going to come down with the LED, the capacitor, and that will tell us if our circuit is on. It still means we've got 18 volts here. And we need 12. But that's easy to overcome. If you think of it, sorry about the shaking there. We need 12 volts. 12 volts is 2/3 of that. So if we put two resistors here, like that, and we make this one 2/3 bigger than that one, we'll get 12 volt AC there. I know it was a little bit tedious to go through all this maths, but it's important. I must stress we are going to be working with mains voltage here. This is 230 volt AC at 50 Hertz in South Africa. Please, if you don't know what you're doing, don't play here. Interesting enough, with this, we've created an isolated output, if you want to think of it like that, because whatever's happening here on our mains is isolated through this transformer. It'll become nice to see later on, if we put a scope on this, why this isolation is quite good. The formulas are not difficult, the formula is not hard. Keep them in mind. Sorry, I've just realized before we do go on, I need to explain one more formula to you. We said we're going to put in 3 microfarad of capacitance here. Now, that's not normally a standard size of capacitor. And if you remember from school physics, if you put resistors in series, well, let's call it R1, R2, R3. The resistive total would be R1 plus R2 plus R3. Or don't fall off. If we put resistors in parallel, R1, R2, R3. The formula became 1 over R1 plus 1 over R2 plus 1 over R3. Capacitors are the inverse of resistors. If I put capacitors in parallel, then the capacitive total becomes the sum of the capacitors. If I put capacitors in series, it becomes the reciprocal of the reciprocal of the sum. Just something to keep in mind. So our little circuit here, I'm going to have to put in 3 1 microfarad capacitors to achieve that. Putting in the 3 1 microfarads in series will give me in parallel will give me the 3 microfarad that I need. Right, let's get our components out and build this thing. So here are our components to build this circuit. We have these 1 microfarad film capacitors. We have 3 of them. We have our little LED to tell us if the circuit's on. We have our little metal film resistor, 100 ohm. We have a double pole, double throw switch, and I have a fuse holder that I just need to put in. And then we have our transformer. The board I'm using is just a prototype board. It's a strip board, Vera board, whatever you call it. Just strips on the back so we can put our components in, place them, and we can drill out little portions that we don't want. So I'm going to go ahead. I'm going to build this offline because I think to watch me solder and drill out things is just tedious. I will show you how I solder surface mount components and how I'd place it. It's easy. These little devices you would want to put on first, and then the highest standing devices, you know, second, and so you build up and you go higher until you've got the highest one, so you can balance the board. Yeah, let me get on with it, and then when I'm back, then we will have a working power supply. So just want to give you an idea on how I'm soldering this stuff, so you can see our strip board a bit better. And yeah, let me make sure I've got the right thing under the mic, under the camera. What do I do? Heat. That's it. Do another one if you want. Can you see it over there? Simple. Very easy to solder through all components. What you will see is on these resistor leads, I've bent them out. That's just to hold them in place. Makes it easier for me to solder. So I'm going to go up and finish soldering this board where I can actually see easier, and we'll come back to the finished thing. Remember, always clean your tip and always put some solder on it. Always tin it. You don't want it to pit. Cheers. And there we have it, boys and girls. It's a brand new day. Unfortunately, I had to stop filming yesterday as the light was getting a bit low, and I don't have enough artificial light to film after, or when it's dark, so I'm going to have to clearly remedy that and get some more lights. Either way, our AC mains is coming in here via that toggle switch down there. We go through our fuse, we come into our transformer, and the output of the transformer, we put the 2 coils in series to give us our 18 volts, because they're two 9 volt windings. We come through our middle resistor, our current limiting resistor, through our LED, through our 3 capacitors in parallel, and that just goes back to the second winding, the secondary. When we did the maths for this, we assumed it was 2 9 volt AC coils, and it would be, or 2 9 volt AC windings, and it would be the same under all load conditions. And clearly I didn't read the last column in the data sheet. The data sheet tells us that these 2 secondary windings are actually unloaded. They will be 12 volt AC. So we had our 100 ohm resistor in there. When I powered it on, this LED came on brightly for a second or two and then burnt to hell. So all I did is I've upgraded this resistor from 100 ohm to 1 kilo ohm or 1000 ohm to limit that current and to cater for the 2 secondary windings being 12 volt AC unloaded. All I've done is I've mounted the Vera board on these little offsets that I had, just to keep the bottom end off the desk or whatever. Nothing really fancy to this. To show you that it works, what I'm going to do is I'm going to hook this up to our oscilloscope so we can actually see the voltage waveform in the time domain. Just a word of warning, this transformer is isolating my mains, so typically with an oscilloscope you need to think of the ground lead as actually being mains earth. So you cannot just hook up your ground lead of your oscilloscope to anywhere in the circuit and hope for the best, because what you would do is you would bring that point in the circuit to mains ground reference. That is why it is very, very dangerous to your oscilloscope leads, and even to you, to start probing around here on mains voltage if you don't know what you're doing, because you have a 50% chance that this is actually the live wire and that this is actually the neutral wire. It could be that somebody wired your house wrong and actually swapped this in a plug, and that is actually your neutral and that is your live. Now if you go and hook your oscilloscope ground onto that, you will bring that point to mains earth, which would make your oscilloscope the fuse. Expensive fuse, but nonetheless. So anyway, I'm going to hook up my oscilloscope. Important, this transformer is isolating mains, so I can actually hook up my oscilloscope ground here as my reference point. Just something to be aware of. So let me get everything hooked up and then we will get the camera on. And see, just to prove that I don't work in isolation, I do have my 2 supervisors looking after me. My 2 QC engineers are clearly not very impressed with my latest design, and they've decided to take a nap on it. Oh well, we'll have to redo that one. Okay, here we have our oscilloscope hooked up onto the secondary side. We're just measuring across, for want of a better word, the neutral of that side and the live, so the full output of both secondary windings that are in series. Interesting enough, you can see the LED flickering. Well, that's because it's switching on and off at 50 Hertz. So remember, it's only on for half the cycle, so it's actually switching at 25 Hertz. On the oscilloscope, we've got it set for 20 volts per division, and we can actually see we're getting 24.2 volts RMS output at 50 Hertz. So oscilloscope is a very nice tool to see voltage changing in the time domain as it changes over time. Now we reversed engineered our NEMTEK board to we worked out that we need 12 volts AC RMS based on the capacitors and whatever. Now that wasn't a completely useless exercise. I haven't actually been able to find much information on that board except an installation manual. And importantly enough, what I don't see on that board is I don't see any input for mains, AC mains, and what I can gather from the installation manual is it has a battery input that would come directly from your batteries and power up this board in case of mains failure, but it has an AC input of 18 volts. And that was the AC input where we repaired the diodes and those sort of things. So what I'm going to do is I'm going to get the Energizer board. We're going to do it two ways. I'm going to use my bench power supply to power up or to simulate the battery input, which I'm going to presume is 12 volts because that's what I gather from the installation manual. So we're going to power that up from there, and what we're also going to do is we're going to just solder two little leads from our power supply to the AC mains, well not AC mains, to the AC input, the 18 volt AC input of this. Okay, we've got our power supply hooked up, and let's just set our white balance there. So what I'm going to do is I'm going to limit the amps, the amount of current we can put into this thing. I've got it set to 12 volts. Up here is a little jumper that we need to switch it on. See, when I short it, those two little LEDs come on and they go off. Clearly not enough power. Let's turn it up a little bit. Relay clicked in. It's holding it in. Okay, let's just turn our current up a little bit because it's pulled our 9 volt or our 12 volt rail down to 9 volt, and it's pulling the full 300 milliamps that I'm limiting it to. Let's give it a bit more. Some sort of buzzer. I could smell the magic smoke. I don't know if you saw that, but that little transistor down there decided to give up the ghost. So clearly we still have a short somewhere. Okay, we've managed to switch it on. So looks like we still have a fault down there. And so, boys and girls, we keep going down the rabbit hole here. I've removed that little mob that was down in there where we're focused at the moment, and you can see there's some little capacitor here hanging in the breeze. And yeah, looks like another fault. What is interesting now, when I switch this circuit on, the relays click in, and we have no flashing alarms. So what I'm going to do is I'm going to take out this connector here, clean that up, and see just what the problem is down there. Yeah, interesting. Multiple faults. One transistor missing, two faulty transistors, a faulty diode. Now, let me take that out, clean it up, and we'll come back in the next shot. Okay, boys and girls, and there you can see where our little capacitor was that was underneath there. I've just cleaned up those pads. I've taken out the connector so that I could do that. So I'm just going to replace that little capacitor offline, because it is a very tiny component, and once we're done with that, we'll just come back to the shot when we've cleaned it up, and we'll see what else is wrong from there. Okay, we're back. What I've done off air, just quickly, if you remember in part 1, we replaced that transistor down there that had gone for a loop of, yes, it was blown in half. What happened when we switched this thing on now, that transistor over there, which I didn't see, actually had a hole in it, so it was also stuffed. So what I've done is I've just replaced that. So what I'm going to do is I'm just going to switch the board around, we'll come back and we'll see if this thing actually switches on the outputs. Unfortunately, I can't test the high voltage side of it because this board plugs into something else, and that connects to all sorts of other things. So the owner is going to have to check that side of it, but I don't, after I repair on the rectification circuit upstairs, I don't believe that's a problem. So what I'm going to do is just switch this board around, and then we can have a look at it. And so, boys and girls, it looks like we have come to the end of our repair. I've replaced this little MOV over here and reseated the capacitor that was underneath it, 100 nanofarad capacitor. I've also wired in the AC mains with our test circuit so we can check that, and I've replaced these 3 transistors. If you remember from the first episode, the middle one was the one that had blown into half, and as we were carrying on with our fault finding, we found the one on that side, the left hand side of the board, and that was also shorted, and this other 3rd transistor is also finished. So all that's left for me to do now is switch on the mains through our little circuit, and we can see the board powers up. Now obviously I'm sure some of these are warning lights and errors, and I have no idea because I don't have the rest of the circuit. But what I can do is I can switch on the battery side, and what I expect to see after a bit of time is that we get some sort of alarm. So I'm just going to short out this jumper to switch it on. Helps if I, yes, bench power supply. There we go. On. So all that's left for me to do now is to clean up this board, resolder this little terminal connector here. It will go down on the bottom, and then give it back to the owner. Obviously we have to finish our review of the Darling Brew, the slow beer, so I'm going to set that up, and we'll chat about the Darling Brew next. But yeah, the thing with this board, don't get caught going down the rabbit hole. You'll see it's quite wet because I've been spraying it with IPA, because I was just checking what heats up it will make the alcohol evaporate. And down here still wet, and up here also still wet, so that's fine. I know those transistors are switched on, and yeah. Oh, what you can't see is there's a little, there we go, a little green LED that tells us our power is on. And obviously the red and the amber LED are telling us there's some sort of fault, it's missing something. So cool, let me set up the shot, and then we'll wrap up with our review and rating of the Darling Brew slow beer. Okay guys, it looks like we've come to the end of a successful repair of our NEMTEK Mxx Stealth Energizer board. Quite a few things wrong with it. Transistors that switch relays that had for some reason blown up over voltage typically. The capacitor was misplaced, and a diode in the bridge rectifier circuit. This board can go home now to its owner, and hopefully he'll be happy with it. Our beer under review, the Bone Crusher by Darling Brew. It is yeah, it's really, like I said earlier on in the video, I probably tasted this beer about 5 years ago, and it was really, at the time, one of the beers on the market. It was really one of the better ones. It's supposed to be a Belgian or Flemish style beer, Belgian wit or wit. A wit beer to me is a very subtle beer. It's a stylish beer. It's elegant. It's like a classy lady. It's not overpowering. So my notes, my take on this beer, Belgian Wit, style 24A in the BJCP style guidelines. For me, the taste, I'm getting a very nice tart, acidic taste out of this beer. Bear in mind, this is just out the fridge, so it's a bit chilled, and I would advise you, if you're drinking craft beer, to let it warm up a little bit. You get sometimes the flavors that you wouldn't normally get. So I get a tart, acidic sweetness, a little, definitely a cereal a cereal taste out of it, like a wheat. It's a very crisp beer. There's something in here that's very citrusy, and not overpowering. It's just there. It's very nice. The aroma, definitely, you know, these guys have used wheat and Pilsner malt. It's a very wheaty, malty smell. It's difficult to explain. Like straw almost. What I do get as the beer warms up, so I get a aroma of candy floss, cotton spun candy. If you went to the fair when you were a kid or as an adult and you buy your kids, or you had that candy floss stuff, that smell of that, you definitely getting in here. That tells me they've used one of the Belgian specialty malts to bring that aroma through. Very good. What you don't get with this beer, there's no hop aroma. There's no overpowering aroma from hops. There's no overpowering bitterness from hops. The hops in this beer, in my opinion, are very subtle. They've been kept to a minimum. I would guess they're only doing a bittering addition, and even then very, very little. The thing with this beer is the malt profile really shines through. Yeah, that cotton spun candy. One thing, but I think that's a byproduct of the wheat malt. Sometimes you get a aroma, especially when you use wheat as your base malt. You get a alcohol with like a fusel alcohol. You have to be very careful with that, because that's typically that comes from the wheat, and you shouldn't confuse it. And yeah, as the beer is warming up, I'm getting definitely more of that cotton candy. It's actually quite nice. A mouthful. I'm going to go with a medium body on this. It's got quite a bit of body. Like I said before, it's very tart. It's got quite a acidic feel to it. Those things make it effervescent. They make it very refreshing. So, I mean, you can see. Appearance pale straw. Yes. Well, yeah, I'd give them that. It's definitely on the straw side. The thing though is the head. I personally expect a larger head with a Vitby. Other than that, I think the beer is very well made. I would say they've put in a medium carbonation to this, which is fine. It helps. The CO2 helps with that acidity, that taste of the appearance of the acidity. So Yeah. If you wanted a commercial example of this, probably for me the closest you could catch or buy would be a Hoergaarden Wit. You can get that at any liquor city. They're quite common. So how am I going to rate? So how am I going to rate the Darling Brew Bone Crusher? As far as the style goes, I think they've done a very good job here. The only minor flaw really is the head. I think as far as the style guide goes, I'm going to give them a 3.8 out of 5. Now, there is nothing inherently wrong with the beer. It's a very, very, very good beer as far as the style goes. I think it holds its own. I just think, for me, the mouthfeel, the body of the beer is too much. This is a beer. I mean, you can see in this review, I've potted this beer almost. It's a beer that's supposed to be very drinkable. It's refreshing. The problem when you have a high mouthfeel, a high ending gravity, is you can only drink so many of them. You know, it doesn't become a session beer anymore. I don't think a Wit is supposed to be a session beer, but you never know. If you end up with a bunch of Flemish people, what can happen? So yeah, I will stick with that on the style guideline. For my drinkability, and drinkability, as we know from episode 1, is how many of these things can I drink in a row, or would I be happy drinking this thing in a row? I'm going to give the Darling Brew Bone Crusher a 4 out of 5 for drinkability. It is a very refreshing drink. It's got a nice effervescence that's going on in it. And yes, I could probably sit and polish off 6 or 7 or 8 of these things in a row, and it would just be spot on. The problem is, it's not Darling Brew's fault. It's the acidity of the beer. You can only, I can only drink so many of these, and then I'm going to get heartburn and whatever. But I really think they've made a good beer here. Cheers. Now, this is the end of part 2 of our Mxx Energizer board repair. I'm sorry I didn't go down or show you everything that I was doing behind the camera. Unfortunately, I have a little gorilla thing tripod on my bench, and it makes it very difficult to film. I don't want to bore you with all the engineering maths, but I think if we understand a little bit of the basic maths and we can actually see it on the oscilloscope, because it's a good way of visualizing it, then I hope you learn something from me. In the future episodes, I'm going to try and work on my lighting and tripod setup, that you can actually get a feel or a view of what I'm seeing, because it's, you know, I look at the circuit and I say, yes, it's this, and that's it, and off we go. And I don't think that's really the right way to learn from me. I think I need to spend more time explaining to you what the different components do, why they do them in a easy to understand way, and then actually show you how they're doing them. You know, doing what they're supposed to do. You know, I have the test gear behind me. It's nothing to hook up a scope and show you an AC waveform being rectified to DC or whatever. We repaired the board successfully. The things you need to keep in mind when you're looking at anything that's installed outside: be aware of something like a lightning strike in the vicinity. Now please understand, if you have a direct lightning strike, you're going to bring me the ashes of the board. If you have a lightning strike in the vicinity, you would have a potential difference rise in the ground. That's what's going to kill your board. Things to look out for: semiconductors. They really don't like a lot of over voltage. They don't like high currents. They can only absorb the current that is injected to them, but they don't like a lot of voltage. We were lucky with the board repair, because they blew, or with the lightning strike in the vicinity, they blew components on the surface. They didn't damage too much of the track work. Be careful not to go down the rabbit hole and chase your tail with these things. It takes a logical progression from one part of the board to the other, and if we understand how we got to the other part, that's great. And of course I cocked up because I didn't bother reading the user manual, and seeing that there was an 18 volt AC input, great, shoot me, I don't mind. But we did some useful maths that might help you if you ever want to design something that doesn't fit whatever your transformer holds. As always, be careful when you're working with AC mains. It's dangerous. It has the potential to kill you, and if you're not comfortable with it, or you don't know what you're doing with it, don't do it. As always, if you like the video, if you learned something, give us a thumbs up. If you don't like it, give us a thumbs down, doesn't bother me. If you want to see more of these types of videos, please hit the subscribe and the bell notification below, and you receive more videos from us. Catch you next time. Cheers.